And can you see my icon when I point things out, my cursor? Okay, that's good. I have a little pointer there. So
yeah.
All right, we're live on YouTube and we're recording, so whenever you want to start, you're welcome to, Roy.
Okay, let's give it another minute and then let people drop in, and then I'll start. All right, everyone. So good morning. Let me just start with something that needs to be said. So these events are being recorded and will be live on the IQuish YouTube channel. For bandwidth purposes, we would like to request you to keep your microphone and video off until the end. Should you have any questions during the presentations, I will watch the chat box and will interrupt the presenter at the appropriate time. Otherwise, please feel free to ask your questions following our speaker's presentation. So with that being said, everyone, good morning. It's my great pleasure to introduce Sandy Irani from UC Irvine and the Simons Institute. So Sandy graduated with a degree from Princeton in 1986, upon which then she went to UC Berkeley and completed her PhD in computer science in 1991. The following year, she was a recipient of the University of California's President's Postdoctoral Fellowship. And then fall 92, she joined the faculty of University of California, Irvine, where she's currently a full professor. She served as chair of the computer science department from 2005 to 2008 and from 2010 to 2012. In the first part of her career, her research focused on online algorithms and their applications to scheduling and resource allocation. More recently, she has been working in quantum computation with a focus on quantum complexity theory. She is the author of a web-based interactive textbook replacement on discrete mathematics in collaboration with ZBooks, Inc. She is the 21-22 recipient of the UC Irvine Distinguished Faculty Award for Teaching and also a fellow of the Association for Computing Machinery. So it's my pleasure to introduce Sandy again, who's going to talk about Hamiltonian complexity for finite and infinite quantum systems. Thanks, Sandy.
all right, thank you, Roy, and it's really a pleasure. Thank you for inviting me to speak today. I'm sorry I can't be with you all in person. I'm going to be describing joint work with Dorit Aharonov, and that appeared recently in the last thought conference. So, my advancing isn't working. There we go. So I'm going to start with a really standard problem in computer science and optimization. The input to our problem is n finite valued variables, and we have m constraints. And the constraint is just a function on a small subset of the variables. And what we're looking for is a global assignment to all the variables, which is just an n-dimensional vector. And for a given assignment, each clause or each constraint has a cost. And that's just the value of the function on the small subset of variables to which it applies.
Hey, did you give me access to the? No,
I'm sorry.
Hannah, can you mute your microphone, please?
Yes, I'm sorry.
Okay, sorry. And so the cost of a particular constraint is just the value of the function on the variables to which it operates on. And the goal is to find a global assignment to the variables that minimizes the sum of the cost of all constraints. So this is just a very general problem in optimization that models just a whole myriad of problems that come up in operations research, physical and biological sciences, computer science, from from protein folding to airline scheduling. So we're going to study this problem from a complexity point of view, and in order to do that, it's helpful to just simplify it a little bit. So we're going to be looking at Boolean variables and Boolean constraints, so Boolean functions, and we're going to be looking, and in complexity theory, it's helpful and makes it easier to study problems that are decision problems, where the answer is yes or no. And this isn't too much of a limitation, because typically if there's an efficient algorithm for a decision problem, then you could use it for optimization or to find an optimal solution. So in this case, we're just asking, is there a Boolean vector that satisfies all the constraints? So in other words, that causes all of them to evaluate to 0. And this is the famous Boolean satisfiability problem. And early on in computational complexity theory, this was sort of a central idea that allowed us to reason about the computational complexity of problems. So it turns out this problem, as you probably all know, is complete for the class NP. And I'm sure many of you have seen this before, but let me review it because we're going to be generalizing it for the quantum setting. So the class NP characterizes the set of problems where a solution may be hard to find, but once you've found it, it's easy to check. So more formally, a problem is an NP if there's an efficient verifying algorithm, and if X is a yes input to the problem, then there's some witness string Y that will cause the verifier given X and Y to accept. And if X is a no instance, then no matter what string you give to the verifier, it'll reject. And so it's not too hard to see that that sits inside NP, because the witness is just the satisfying assignment. So if I give you an assignment to the Boolean variables that satisfies all the clauses, it's really easy to check that. So now, famously, back in 1971, Cook and independently Levin proved that SAT is complete for the class NP. And so what does this mean? It means that SAT can express any problem in NP. So an efficient algorithm for satisfiability will give an efficient algorithm for any problem in the class NP. Now, just as an historical fact, when Cook proved this theorem, the description of the class NP was not this natural version of verification that I just described to you. The class was equivalently defined in terms of non-deterministic Turing machines, which is a much more sort of obscure complexity-theoretic idea. And while this was seen as an important result, people at the time didn't really understand how central it was going to be to computer science. And then it was my PhD advisor, Dick Karp, who in 1972 came along and said, actually, this is not just something that's going to sit in the corner of complexity theory. Many, many natural problems in OR and computer science that people have been trying to solve are also NP complete. So it actually applies to a huge wide variety of problems. Okay, so now we're going to look at a quantum generalization of this. And in this system, we have n finite dimensional particles. So the dimension of the system, if we're looking at qubits, is 2 to the n, and a Hamiltonian, and we're looking for the lowest eigenvalue of this large matrix, or the ground state, which is the eigenvector associated with the lowest eigenvalue. So the local Hamiltonian problem, the input is the Hamiltonian, which is expressed as a sum of a set of local terms, and each local term acts on only k d-dimensional particles, and k is typically quite small. So the dimension of the system is d to the n by d to the n, but the Hamiltonian itself has a distinct representation. So each of those terms is just a d squared by d, a d to the k by d to the k matrix. So, and the way these two problems sort of relate to each other is if it happens that the Hamiltonian terms are all diagonal, instead of little Hermitian matrix. If they happen to be diagonal, then this is exactly constraint satisfaction. So constraint satisfaction is strictly a special case of the local Hamiltonian problem. So now you can imagine different varieties of this problem. You could change up the locality. So how many different particles does each term act You could look at different particle dimensions. So typically we look at qubits, but you could look at qubits, which are d-dimensional particles, or you could add some geometry to the problem. So as it's expressed now, there's no sense of geometry just because each term acts on a small set of particles. It doesn't mean that these particles can be embedded in some, 2 or 3 dimensional space where these terms act on particles that are close by. But you can certainly add that to the problem, and oftentimes this is done in terms of putting the particles on the vertices of a grid and saying that 2 vertices have an interacting term if they're adjacent. So these are common ways, sort of different varieties of the local Hamiltonian problem that you could look at. So I've given this talk a couple times to computer science audiences, and so the part about entropy completeness I tend to gloss over because everyone's familiar with that. But sometimes the idea of a local Hamiltonian problem needs a little bit more of a sell, probably not with this crowd. But what I do to sort of indicate sort of how fundamental this is on the physics side is I quote a paper by my colleague Steve White at UC Irvine that appeared in Science, in which they study exactly an instance of this problem. So in this case, the lattice is this beautiful Kagame lattice, and they're looking at the Heisenberg antiferrometric model on each pair of neighboring vertices. And they've studied this to understand the properties of the ground state. So they wanted to know, is this ground state a valence bond crystal, meaning that the ground state has these pairs of entangled qubits, or is it a spin liquid? And their findings was that it was a spin liquid, but more to the point from the complexity point of view is that they said a key problem in searching for spin liquids in 2D models is that there are no exact or nearly exact analytical or computational methods to solve infinite 2D quantum lattices. So that's exactly the sort of problem that we're going to be looking at today from the point of view of computational complexity. So how complex is it to find the ground state energy? And we have this beautiful theory of NP completeness on the classical side, and we're going to use the same kind of theory and machinery to study this quantum problem. And so this was, Alexei Kitaev's sort of insight back in 2002 that sort of launched the area of Hamiltonian complexity, in which he noticed this connection between this really fundamental problem that's sort of the bread and butter of numerical science, numerical condensed matter physics, and on the other hand, optimization problems that are well studied in computer science. And we have this beautiful theory of NP completeness to understand the difficulty of those problems. In computer science, we're not so good at proving lower bounds. We believe that NP hard problems are hard to solve, but we have a theory giving evidence that they're hard to solve. So we sort of clump together the problems in this class. So Kitaev noticed this connection and noticed the fact that this sort of fundamental problem that is well studied in condensed matter physics actually is a generalization of the constraint satisfaction problem. So he defined the local Hamiltonian problem formally as you're given as input a set of Hermitian positive semi-definite matrices operating, each of which operates on k particles or qubits of dimension d. They have bounded norm. And each matrix can be specified succinctly. And because from the complexity point of view, we like to study decision problems, we're going to phrase this problem as a decision problem. So you're given 2 real numbers. E is the target energy and a gap delta, which is at least 1 over a polynomial. And you want to know, is the smallest eigenvalue of the resulting Hamiltonian less than E or greater than E plus delta? And this delta is used because we can't actually, you don't expect to be able to compute the energy precisely. So this is sort of a little bit of a gap to reflect the fact that this problem will be solved with bounded precision. From the complexity point of view, the important thing here is that this is actually what we call a promise problem. So if I give you an instance of local Hamiltonian, I'm promising you that one or the other is true, that the energy is at most E or at least E plus delta. And if I make a mistake and I give you an invalid instance, in which the true ground energy is in the range between these two values, the algorithm is not obligated to respond correctly. So this is sort of a way of taking this problem and phrasing it as a decision problem so that we can study it from a complexity point of view. And when Kitaev introduced this problem, he showed that it's complete for the class quantum Merlin-Arthur, which is a quantum version of NP. So we have the class NP. A problem is an NP if there's a polynomial time verifier, X is in the language, there's a witness that causes A to accept. If X isn't, for every witness, the verifier will reject. And so there's a natural sort of quantum counterpart to this definition, defining the class QMA. So again, it's a little bit different in that QMA is a class of promise problems. So each problem has a set of yes instances, no instances, and invalid instances, like I talked about in the previous slide. And the problem is in QMA if now both the witness and the verifier are quantum. So X is a yes instance if there's some quantum state on some polynomial number of qubits, such that a quantum verifier will accept with probably at least 2/3. And if X is a no instance, no matter what quantum witness I give you, the probability that A accepts is bounded by 1/3. And this 2/3 and 1/3 is completely arbitrary. There are sort of standard techniques to boost this probability through repetition to be sort of exponentially small. So the error in either direction is exponentially small. Okay, so what does a completeness proof look like? So let's look at the easier case of NP. So when Cook-Levin proved the reduction that SAT is NP hard, the goal is to take a very generic problem in NP, and this is just characterized by the fact that it has a verifier, and to generate a Boolean formula. So for every input X, the problem, we're going to generate a Boolean formula, which is in the form of a set of constraints. And it's going to have the property that it exactly expresses whether X is a yes or a no instance. So if there's a Y that causes the verifier to accept, this happens if and only if the Boolean formula is satisfiable. And the generic reduction takes this verifier algorithm, A as a, for example, a Turing machine, any sort of model of computation will do, and we can build a tableau. And what this tableau does is it represents the computation of A on input X. So you can think of each row of this tableau as a step in the computation. And the row is just a string of values that represents the state of a computation or a Turing machine. The witness bits are free variables. There are some constraints that encode that the input has to be X. There's a constraint that checks that the output is accepting. And the most important point here is that you can use a set of local constraints to make sure that this tableau represents a consistent computation, meaning that each state of the Turing machine follows from the previous one by exactly one step. So this could be done by summing together a bunch of little local constraints, each of which acts on just a small window of cells in this tableau. So that's what the generic NP completeness result looks like in a nutshell. Now, if we wanted to generalize this to quantum, there's a little problem with this construction. So it would be natural to say, okay, I'm going to do the same thing now with quantum. I'm going to have a particle at every cell in the tableau, and each row will represent the state of the computation. Now, there's a problem with this in that, let's say that, let's take a very simple case in which from one step to the other is just the identity. So the computation doesn't change from one row to another. The problem is that we can't check that two quantum states are equal using only local constraints. So we need some other way of sort of representing the sequence of states of my computation. And So a generic QMA hardness takes a generic problem in QMA. Now it's characterized by a quantum verifier. It takes an input and produces an instance of a local Hamiltonian, which is a Hamiltonian with thresholds. And we want it to have the property that there's a quantum witness state that causes the quantum verifier to accept. If and only if the ground state is less, I have put 0 here, but it's actually less than some particular energy value. And so instead of using this tableau method, what Katayev came up with, and this is sort of the idea dates back to Feynman, is that we're going to construct a ground state we're going to construct a Hamiltonian whose ground state represents a computation where the different steps of the computation are represented in quantum superposition. So there are 2 registers. One register encodes a clock, and the other one encodes the quantum state. And we're going to construct a Hamiltonian whose ground state looks like this, where it's a uniform superposition over different points in time. And so this clock register represents in unitary the t different steps of a computation. And the computation register starts with some initial state, and each step of the computation is represented in the computation register corresponding to that state in time. So the Hamiltonian enforces that any low energy state has to correspond to a valid accepting computation. Now, how do we go about doing this, and what do these local constraints look like? Suppose that the teeth gate applies the operator U, say, to qubits 1 and 2, just as an example. So we want a constraint that says for every state of the form here, where this is a particular point in time t, and we start out with qubits in state Q1 and Q2, the following state has to have equal amplitude. We're advancing the clock, and we're applying the gate. And note here that Katayev's original QMA construction is 5 local, and it's on qubits. So I can represent this clock using qubits, and the computation is also on qubits. So, and the term itself looks like this. So the ground state just has to be the ground state of this particular operator. So the whole Hamiltonian kind of looks like this. So there's the big matrix, and it's block diagonal, and each block corresponds to a different possible initial state, including the witness. So you can think of coming up with a basis of possible initial states. And each particular square is this particular matrix, which is just the sum of all of those little local terms, advancing the clock and applying a gate. And this is what the matrix looks like. So the ground state of this submatrix is the equal superposition of all of these states, and that has energy 0. And then finally, there's an additional term that adds a penalty term if the output of the circuit is 0. So what this construction ultimately gives you is the fact that if there's a witness that causes the computation to accept, then one of these blocks will correspond to that witness. And I won't have this +1 here because the output of the circuit will be 1. And it will have a ground energy of 0. And otherwise, it'll have a ground energy of 1 over polynomial. So Katayev's construction was great. I mean, it gave us a way to sort of talk about the computational complexity of local Hamiltonian problems, but there are a number of ways in which the construction itself is non-physical. So, for example, it's not translationally invariant, meaning that the term applied to every 5 cluster of particles is different for every set of 5 qubits. It's not geometrically local, meaning that there's no way to embed the qubits in some 2 or 3 dimensional space and have the terms only act on qubits that are close to each other. And it's 5 local, which is, typically the Hamiltonian studied from the condensed matter side are more often 2 local. So since that time, there have been a number of advances that show that even if you apply some of these constraints to the Hamiltonian, it still remains difficult. So local Hamiltonian remains QMA complete, even if you're looking at 2 local qubits on a 2D grid, and even 2 local qubits on a 1D chain. And the 1D result was a bit surprising, partly because, first of all, in the classical counterpart, a 1D constraint satisfaction is actually easy to solve by dynamic programming. And also numerically, condensed matter physicists have had enormous success solving 1D problems heuristically using DMRG developed by Steve White at UC Irvine. So in the worst case, it can be difficult, but in this 1D case, it sort of runs contrary to the intuition that it should be somewhat easier. And these sort of geometric Hamiltonians achieve this result by sort of distributing the clock state. So part of what makes Katai's construction not geometrically local is that you have this clock register and this computation register, and those qubits could potentially be distributed around space. And so the idea is to create particles where the clock state and the computation are sort of the Hilbert space of a single particle encodes part of the clock as well as part of the computation, and then sort of distributes the Hilbert space in a different way. So now let's talk about translational invariance. So another thing about these 2D and 1D results is they're highly translationally dependent. So in other words, if I'm looking at this 1D chain, the particle that the constraint that I'm applying to particles 16 and 17 is completely different than the constraint applied to 17 and 18. And it's much more natural in physics to study Hamiltonians that are translationally invariant, meaning that the term applied to each pair is exactly the same. Now, this poses a challenge from the point of view of studying the problem from a complexity perspective. So in computational complexity, typically we study the running time of an algorithm as a function of the size of it, which is the number of bits to specify it. And when you go to translationally invariant systems, all of a sudden the number of bits it takes to specify the instance becomes exponentially smaller. So all I need to tell you in order to specify a translationally invariant Hamiltonian is to tell you about the term, which is potentially a constant size matrix, and tell you the number of particles in the chain. And now the input previously to describe the Hamiltonian on n different particles, the number of bits required to describe that input scales with the size of the system. And now the number of bits I need to specify the Hamiltonian input is log of the number of particles in the system. So the size of the input has gotten exponentially smaller. Okay, so we actually study kind of 2 different varieties of translational invariance in the literature. So in the first, let me go back. The first version, the input includes the dimension of the particle, the size of the system, as well as the Hamiltonian term itself. So you're asking how hard is it to compute the ground energy as a function of the particular Hamiltonian itself. And in a much stronger version of translational invariance, the Hamiltonian term itself is just a parameter of the problem, and the only input is the size. And this sort of represents the fact that, say, when you're studying the Bose-Hubbard model, that's considered a completely separate problem than, say, studying the AKLFT model or the Ising model or some other model. So each particular term denotes a different problem. And now I'm just asking how hard it is to compute the ground energy of the system, just telling you the size of it. So this has been studied in the finite case. So if I were to formally define this problem for the finite case, the parameter of the problem in the stronger version of translation invariance, the parameter of the problem includes the Hamiltonian term, which is a d squared by d squared matrix, and two polynomials, p and q. So the only input is n, the number of particles, and now this is a 1D system. So the size of the input is log in the number of particles in the system. And now this is a decision problem. So when we apply this single Hamiltonian term to every pair of neighbors in a 1D chain of n particles, we're asking, is the ground energy less than P of n or greater than P of n plus 1 over Q of n? So notice that the gap here is 1 over polynomial, as it was before. And as it turns out, this problem is also difficult. So one might think that translation invariance sort of makes the problem easier, and it turns out that that's not the case. So we know that this problem is hard for the class QMAX. So now I've sort of, this is a different complexity class than QMA, and it's different only in that I now have exponentially long witnesses and an exponential time verifier. And it's not like the problem got harder, it's just that the problem input size got smaller. So this is still scaling with polynomial in the size of the system, but thought to be still hard for a quantum computer. And the idea with this translation invariance is, so the only information that you're given is the size of the system. So we have to translate that size of the system. In order to prove hardness, we're sort of using the Hamiltonian to express some difficult problem. And we're embedding a quantum process in this Hamiltonian, as we did with the QMA hardness. And now we need to translate the system size into a binary number and then simulate a quantum verifier in the Hamiltonian. And in this case, the verifier is the quantum Turing machine, which works well with the translation invariant property. Okay, I just saw that there were some things in the chat. So now we know that the local Hamiltonian problem is hard, even if 2D, two local qubits on a 2D grid, two local in one dimension, and even translationally invariant in one dimension. Now, all of these problems look at finite systems. So they study the complexity as a function of the system size. And that, again, differs from what one typically does in physics. So I think in physics, what you're interested in, you have some models, some 2D terms. And what you're really interested in is what are the properties of the ground state as n goes to infinity. The size of the system itself is somewhat arbitrary. I mean, by necessity, you have to look at, when you're simulating a quantum system, you have to look at finite systems, but the size itself is considered somewhat arbitrary. And what you're really interested in is as n gets large. And the quantity of interest here is the energy density. So if I look at the Hamiltonian on an n by n finite grid, I'm interested in the ground energy of that Hamiltonian divided by the number of particles and letting n go to infinity. So this is the energy per particle as the system is large. And infinite systems, or the thermodynamic limit, has been studied before. We know several things. So in a breakthrough result by Cubitt, Perez Garcia, and Wolf, later improved to 1D by Bausch, Cubitt, Lucia, and Perez Garcia, they show that it's actually undecidable. If I give you a Hamiltonian term and I ask you, does the resulting Hamiltonian applied in the thermodynamic limit have a spectral gap, this is actually an undecidable problem. connecting again sort of complexity theory and the local Hamiltonian problem in an unusual way. It's also studied, we also studied it in the context of this sort of weaker notion of translational invariance. So if the input includes the Hamiltonian term and some precision parameter n, asking whether the ground energy density is below some value or greater than another is still difficult. But it seems sort of unnatural to have the complexity depend on the Hamiltonian term. So typically, as I said, we really think of different Hamiltonian terms as different problems. And if we make the Hamiltonian term sort of a fixed parameter of the problem instead of part of the input, it allows us to study sort of difficult versus easy Hamiltonian terms or models. So going back to this picture, in finite systems, we have these two versions of translational invariance. One is much sort of richer in terms of the input and seemingly more difficult, where you're given the Hamiltonian term as part of the input, and the other one where the Hamiltonian term is the fixed parameter of the problem, and the only input that you're given is the size of the system. Now, when we move to infinite systems, we have a problem. So when we move to infinite systems, the n goes away because we're looking at infinite systems. In the first version of translational invariance, you still have an infinite family of Hamiltonians because it depends on the Hamiltonian term itself. Once you remove the system size from the stronger notion of translational invariance, now you just have one Hamiltonian, and you're looking at it in the thermodynamic limit, and the ground energy density is just a number. So how do you even study the complexity of computing a single number? So here's the problem that we look at. So it's a function version of this problem. So fixed parameters of the problem are Hamiltonians applied in the horizontal and the vertical directions. The only input is n, a binary number. And what n is telling us is the precision to which we want to compute this ground energy. So we're going to output some value alpha that's within 1/2 to the n of the true ground energy. So you can think of it as like computing the first n bit of this ground energy. So now this is studying how hard is it to compute the ground energy as a function of the precision to which you want to compute this. And again, we still have this problem of how to study the computational complexity of a single number. So there are two things that have changed here. One is that we've moved to a function version of the problem instead of the decision problem. And the other one is we have to grapple with is how we even sort of talk about the hardness of computing just one number. Okay, so stepping back to the, let's talk about the first one, the fact that we've moved from a decision problem to a function problem. And let's look at this in the easier setting of just NP completeness. So I'm going to give you a sort of similar to constraint satisfaction that I talked about at the beginning, the M clauses on Boolean variables, weights associated with the clause. And we want an assignment that minimizes the sum of the weights of the violated clause. So each clause evaluates the 0, 1, and the cost of an assignment is the sum of the ones where they evaluate to 1. So I can have a decision version of this problem that asks, is the optimal cost less than some threshold? And T, the threshold, is part of the input. Or I can just ask the function version, just tell me what the minimum cost solution is. And from the complexity point of view, these actually are complete for different classes. So the decision version is complete for NP. Again, it's not hard to verify that a solution is less than T for some particular solution. And the function version is complete for this funny class that has this NP in the sort of like an exponent. It's actually an oracle class. So let me just kind of say what this is. So what this complexity class is, it's the set of problems that are computable by, the F just represents function. So FP are functions computable by a polynomial time Turing machine or computation. So instead of looking at decision problems, I'm outputting a value. And this NP means that I have access to an NP oracle. So at any point in the computation, my computation can stop, put together an instance of Boolean satisfiability, hand it to the oracle, and get the correct answer back. So it's got access to a decision version of the problem. So it's not too hard to see how the function version problem sits inside this oracle complexity class, because I can just use my oracle to binary search. So I want to know the optimal cost, and I can binary search on the range from 0 to an upper bound on the cost of any solution. And the queries are of the form, is the min cost less than some threshold t? I can just, at each step, sort of, I can cut the interval of possible solutions by half. And as it turns out, this is the correct complexity. So if I have time, I will say a bit later about why it's complete for this class. So in other words, function problems are going to give rise to these funny sort of oracle complexity classes. And what we proved is that function GED is contained in, and I'm going to I'll unpack this alphabet soup for you in a second. Function exponential time are functions computable by exponential time classical Turing machines. And they have access for the upper bound. There's access to an oracle called for QMAX. So these are yes instances that can be verified by an exponential time quantum verifier with an exponential size quantum witness. And the lower bound has access to a next oracle, which is just the classical version of QMAX, meaning that an exponential time classical verifier with an exponential size classical witnesses. All of the X just have to do with the fact that the input has gotten smaller and smaller. These are still sort of scaling with the size of the system itself. So our results aren't tight here. So we have a quantum construction, and it's contained in this class, this quantum complexity class, but we can only show hardness for a classical complexity class. So that's the sense in which our results aren't tight. And the key thing here is that non-determinate exponential time doesn't have invalid instances like I talked about. So it's not a problems problem. And that's sort of the key to sort of the difficulty in getting tight results here. So to see the upper bound that it's contained, it's just, again, a binary search. So we're using a decision version of GED, so ground energy density, and we can use two queries to reduce the size of the interval by 1/2. So input n, and n is expressed in log n bits, and so I want n bits of precision for this true ground energy. It's going to take O of n iterations, hence the exponential time. And I'm asking queries of the form, is the ground energy density less than some threshold or greater than another? And this can be done with a query precision 1/2 to the n. So that's the binary search version. And now let's talk about the fact that we're taking, for this hardness result, we're taking this infinite function. So f is a function that's defined on an infinite set of strings, and we're embedding it in a single number. So function GED is just one particular number. And the way we do this is that we encode the output for different inputs in different portions of the infinite binary representation. So the key thing about the ground energy is that it can be specified. It's a number that requires infinite bits to specify precisely. And so I can use that infinite binary string to encode the value of my function for different inputs. I should just, at this point, say that Watson and Cubitt also studied this problem. They encountered exactly the same issue that we did in terms of not being able to get tight results, and they resolved it in a completely different way. So their results are quite different from ours, but they started out with the same sort of looking at the ground energy density from a complexity point of view. I want to check my time here. So both constructions, how do you even deal with the infinite grid? Both constructions use this beautiful construction by Robinson, and this was first used by this result by Cubitt, Perez, Garcia, and Wolf, in which they used Robinson tilings, which create this sort of asymmetric pattern of squares. And tiling rules are just a classical Hamiltonian. So on top of this, they layer a construction that allows you to get sort of an infinite family of problems. I think what I'm going to do in the interest of time, I don't think I have time. So basically, our problem on the infinite plane reduced to a function version of translationally invariant Hamiltonians. Here's the finite version of it. So I have problem parameters, Hamiltonian term and a constant, and input n. And I want to know if I apply this Hamiltonian term to every pair of qubits in a chain, I want to output a value that approximates the ground energy of that system. So this is sort of a function version of the translationally invariant decision problem that I mentioned earlier. And again, we have not quite tight results. So we proved that this is inside the class FP to the QMA X and hard for a classical complexity class. And I think what I'm going to do is, because I'm at the end of my time, I just want to finish up with an open problem, which is sort of the difficulty that we encountered in proving a hardness result using a quantum complexity oracle class. So here's a very simple version, which is a very natural problem that we don't know the complexity of. So it's the function version of local Hamiltonian. The input is a local Hamiltonian at n qubits, so it's no longer translationally invariant. It's a finite system, just a simple local Hamiltonian problem, as described initially. And instead of framing this as a decision problem, I just want to frame this as a function problem. So you're asked to output an approximation to the ground state, where your approximation has to be within 1 over a polynomial of the true value. And we don't know the true complexity of this. We know that it sits inside FP to the QMA, because I could use the QMA oracle again to binary search on this value. But we don't know how to prove hardness for this complexity class. And the problem has to do with the fact that QMA has invalid instances. So we're encoding a computation in a Hamiltonian, and we want the ground state to represent the true minimum energy, and it's very hard to do in the presence of these invalid queries, which have completely uncontrolled outputs. So, so I'll leave I'll end here with this open problem, which is a really sort of fundamental problem. I think actually captures in some ways better the complexity that people are interested in than the decision version, and leave it as an open problem. So thank you for your attention, and let me know if you have any questions.
Perfect. Thank you, Sandy. Excellent talk. Very good.
Should I stop sharing at this point?
Let's wait a minute, because people may want to go back to a previous slide or something. Yeah. So I guess let's start with Brian. I saw his hand go up first. Yeah.
Okay, great. Thanks for the nice talk. I guess the question I had, presumably these hardness results about the thermodynamic limit say something about the convergence of the energy or energy density as a function of system size, either that it doesn't converge or it converges in a way that we don't understand or something. Is there something kind of
Yeah,
said about that?
So for these particular constructions, it's requiring exactly that. So in order to be able to encode sort of this infinite set of outputs in this infinite representation, it means that it's not really converging in a nice way, because every bit of information is giving you some new information about the function that you're operating on. So these are things that don't converge nicely to a fixed number.
But somehow there's still a well-defined thermodynamic limit, despite the fact that it is bouncing around somehow as a function of n.
Yes. So, so as you get larger and larger, as you sort of grow the system size, you're sort of incorporating more complexity into that number.
Okay, great, thanks.
Marius?
Yeah, well, great talk. I mean, I finally understand something about communication complexity and Hamiltonian. And I'm really curious on even how formulating this correctly in the purely infinite dimensional setting, right? I mean, if I were to have a limit model, maybe I could say something. So I'm asking myself, what is the right way to do that? Should I think of, I mean, it could be easier if I think of this infinite dimensional model. If you go to infinity, you can probably no longer really easily talk about pure states, right? Could be that you have to go to densities, but are you really somehow suggesting that there should be a mechanism? I give you this local Hamiltonian, which is defined on some nice algebra of observables, of course, right? Mm-hmm. And then I'm looking for a witness of the energy, the lowest energy. Yeah, that would probably be a density. I mean, is it even conceivable to have an infinite dimensional model which gives you lambda 0 of h on the nodes? And then
so we're looking at the limit. So for each point in time, there's a fixed finite Hamiltonian. And I think the thing is, because we're always looking at some fixed precision. So at any given time, the input's saying you don't have to compute the entire precise ground energy density. I'm just only asking for a particular precision. All of a sudden, it becomes.
I totally agree, but for n to infinity, that is still 0. So the question is, should I expect that in the infinite situation, I can do it precisely? It's just that, is that even conceivable that I have an infinite solution which gives me the correct number? And then it's a question of approximation of the infinite solution versus a finite. Is that relevant at all?
Yeah, so I think the actual infinite number is something that can't be, precisely stated, and so I think once you go to and ask about a finite precision approximation, all of a sudden that allows you to just look at a finite system, because you can always approximate this infinite number up to a given precision with a finite system. So if I only want precision delta, I can basically look at a system size that's a function of 1 over delta, and that will give me an approximation to within my desired approximation delta. So, I think it's the finite precision here that we're looking at that enables us to sort of limit ourselves to finite systems. But the infinite, the actual value for the infinite.
So you're saying that the problem of, suppose I have an infinite solution which gives me exact value, and then asking what does the smallest support of a qubit which approximate that is an easy problem.
It becomes finite. Yeah. So if you're only, as soon as you limit the desired precision, then you can actually just look at, you don't need the whole infinite plane, you can look at some finite chunk of that to get.
Right, but the size of the chunk is known, or?
Yeah.
And it's polynomial?
If you want precision delta, a 1 over delta squared by 1 over delta squared is sufficient. So we derive that actually.
Okay, good. That's what I wanted to know. Wonderful.
Yeah. Are there any other questions for Sandy? If not, then let's thank Sandy again.
All right,
for,
thank you.
Excellent talk.
Thank you.
Okay, so I guess, let's see here.